Okay, let's dive right into this explainer. Have you ever wondered why the maps you rely on every single day are deliberately hiding their own flaws? Well, that's exactly what we're going to uncover today in Tactical Cartography, Visualizing the Unknown.
It's a pretty serious question, really. Would you trust a map with your life? Picture this. You're a dispatcher trying to route an ambulance based on a calculated travel time. If your system just spits out 8 minutes, but totally fails to communicate the underlying uncertainty in that data, like, traffic light phases, sensor errors, or sudden network delays, it could literally cost lives. We all kind of fall into this trap of assuming our digital maps are these perfect, flawless reflections of reality. But honestly, they're actually just carefully calculated estimates. Tracking a hurricane trajectory is an absolutely perfect example of why visualizing uncertainty is completely crucial in high-stakes situations. Usually, people see that growing white forecasting cone and naturally read it as increasing storm intensity, or they think the physical storm itself is actually getting wider, but that's not it at all. It actually represents the increasing uncertainty of the storm's future path. And this simple visual misinterpretation, it can trigger completely disastrous, unnecessary evacuations. But cartographers can fix this by adding a simple tone value to the cone. By making the higher probability areas darker, it instantly and clearly communicates where the true danger lies without confusing anyone. So our system diagnostic menu for today covers 4 key areas. First, frameworks of uncertainty. Second, the visual arsenal. Third, area and thematic mapping. And finally, number 4, the visualization twist. Let's start with section 1, frameworks of uncertainty, mapping the unknown. Before we really get into the specifics, we have to understand the architectural framework that cartographers actually use to display what they simply don't know. Instead of forcing you to look at split-screen diagnostics, where your eyes are constantly darting back and forth between a standard map and a totally separate uncertainty map, the absolute best method is what we call a coincident representation. Think of it like a holographic overlay. It perfectly fuses the geographical attribute and the cartographer's doubt together into one single integrated map view. So you're processing the reality and the risk at the exact same time. Now we can further divide these integrated maps into 2 distinct strategies. First up, we have extrinsic methods. These are where we add completely new graphical elements to the map, like adding little black arrows pushing out from a location center to encode potential deviations in travel time. On the flip side, we have intrinsic methods. These actually alter the core data itself, like taking a solid boundary line and changing it to a dashed one, just to warn you that, hey, this line is really just an estimate.
Moving right along to section 2, the visual arsenal, points and lines. Cartographers don't just guess what visuals work best. They rely heavily on empirical studies. And based on that research, variables like blurring and tone value are highly suited and just completely intuitive for our brains when it comes to seeing uncertainty. But consider the variables that are not suited for this. Changing a color hue or changing a shape? That's a terrible idea, mostly because we usually read those as completely different categories of data altogether. Oh, and surprisingly, transparency is actually highly problematic. I know, it seems like a great idea, right? But the problem is it renders inconsistently across different digital screens and hardware, which means it could potentially change the entire meaning of the map from one device to another. Wild, right? It is so incredibly interesting how clearly you can see certainty just dissolve into uncertainty, whether it's through a blurring effect or by shifting the tone value. As map markers become fuzzier or lighter, your brain instinctively registers a lack of confidence in that specific data point. You don't even need a map legend to tell you that a fuzzy dot represents an unreliable measurement. And we can apply these exact same parameters to lines too, like a GPS route, a disputed border, or a flood boundary. Using a blurred edge, a progressively lighter tone, or a dashed pattern acts as a sort of visual warning system for bad data. A sharp, solid line projects total authority, but a blurry dashed line tells you to proceed with extreme caution. Section 3. Area and thematic mapping. Engineering disorder. Okay, so the really crucial point here is that while points and lines are pretty straightforward, injecting uncertainty into solid regional areas requires a completely different tactical approach. Let's say you identify regional uncertainty in a land cover map. Your first instinct might just be to make the map colors a bit lighter to show that doubt, but you absolutely must avoid changing the intrinsic color lightness. Why? Well, because if you simply change the lightness of an area's color, someone might mistakenly think a lighter green means a completely different type of forest. It completely breaks the fundamental rules of mapping nominal data. So to solve this, we apply extrinsic grids. To pull this off, cartographers deploy what are called noise crosses right over the map's grid. The larger and denser a white cross is, the more uncertain the classification data is for that specific patch of land. We are literally engineering intentional visual disorder to warn the user. But, and this is key, we are doing it without destroying the underlying color coding that tells them what type of land cover they are looking at in the first place.
And finally, Section 4, the visualization twist. Maps inherently lie.
Just when you think you've totally mastered reading uncertainty, there's a major twist. The digital visualization process itself actually creates new errors. Let's look at the strict hardware and interface limits that distort reality. First off, standard technical drawing accuracy physically restricts tiny details, down to about 0.2 to 0.5 millimeters on a display. Second, thematic generalization forces mapmakers to group complex variables together, which essentially deletes nuance just to keep the map readable. And third, scale false confidence. This one is a massive trap. Displaying data that was collected with a mere 10-meter accuracy on a highly zoomed-in 1 to 5,000 scale map gives users a dangerous false confidence in the precise location. Basically, the digital interface is writing checks the underlying data simply can't cache. Think about geometric generalization. When cartographers smooth out the little zigzags of a hiking path or drop the protruding edges of a building just to make the map readable at a smaller scale, there is a very real mathematical consequence. Your calculated distances and area sizes become dangerously shorter and smaller than reality. Simply by simplifying the visual, the map has effectively lied to you about the true physical dimensions of the space. So, what does this all mean? As the source material puts it, the visualization of uncertain information enables secure decisions. Ultimately, we really have to embrace these cartographic imperfections because, ironically, seeing the flaws, the blurriness, the noise crosses, and understanding those generalizations is quite literally the only way to safely and accurately navigate the data. By understanding this visual language of doubt, you immediately become a much smarter consumer of spatial data. Thank you so much for joining this explainer. Now, I have to ask, the next time you load a route on your device and stare at that perfectly solid blue line, will you wonder what the map isn't telling you?